So now let's get into some standard terminology for defining this radar cross section. Okay. So first of all, the very definition, the symbol reserved for it is usually sigma. Okay. And so what I have over here, there are different definitions in 2D and 3D. Okay. And the definitions are very intuitive. What does it say? So it's the limit that the observation point is very far away. The field observed, so Ez squared r theta, right? So there's a missing bracket here, right? At some point normalized by the incident field at the origin. Okay, and you will see there's a 2 pi r over here, and we'll come to why that 2 pi r is over there. Okay, so the case is very simple. So let's say that I have a aircraft like this, right, and I am standing somewhere far over here r, right. This is the distance r from the origin. This is the value r, this is the vector r hat. Okay. In the case of 2D, this is the definition. In the case of 3D, this is the definition. Again, I'm missing bracket over here. Instead of a 2 pi r, I have a 4 pi r squared, but the idea is the same. Find the field far away. So this field far away is also called far field, right. So it's the far field intensity normalized by the incident field intensity at some point, and the easiest point is the origin. Okay. Now, so there are in the world of radar, there are two different kinds of sort of quantities that are calculated. So let's stick to this example which I have drawn over here. Let's say that this is one antenna over here. Let's say this is air traffic control, okay, and this is another air traffic control over here. So both of them have radars. So the first guy is sending a wave like this to the aircraft, and this aircraft is going to, when the radar wave bounces on the aircraft, it's going to get reflected in which direction? One answer is same direction. It depends on the surface, right? But given a general aircraft or a general ship, what direction will the wave get scattered into? What is the common? This is a common sense question.
It should come back.
It should come back. Okay, that's one answer. Any other answer? It will go everywhere, and why? Depending on the shape of the object, right? So if there is some facet which is angled at a certain way, the wave will go off. At the same time, so will there be any wave in this direction? There could be, because think of the spot size of the radar beam. When it hits, let's say the tail fins or something, some diffraction can happen. It can go in basically all directions. So the scattered field energy is going everywhere. In 2D, it's going over 2 pi. In 3D, it's going over the entire 4 pi stereo-radians. Okay. But what do you have that comes back to you? So those are two different imaging modalities, right? So monostatic means transmitter and receiver, same position. That means this air traffic controller sends a wave, and the object is over here. Let's just call it object. This receiver, obviously, because it's standing at that position, it only collects what is coming back to it. So everything else that is going, what happens to it? It is lost. Okay. So that this is called a monostatic. Mono means just one, right? So one transmitter and receiver at the same location. So this is a monostatic radar. The other term for it is, the other kind of imaging modality is bistatic, where you can have, like I drew above over here. So one transmitter object over here, and let's say another receiver over here, right. So I have Tx and Rx are different. Yes, good catch. So this should be scattered, not squared. The squared is already outside, so this is scattered. Scattered field far away, either in 2D or 3D. Okay, right? Question? But is the idea clear? So these are just definitions I am giving you. Okay. Oh, there's another typo here. Excellent. This is far field. This should be R infinity. R tending to infinity. Yeah. Yeah. So notice that in the definition of the RCS, the angle at which the receiver is here. So this is the RX angle, and this is the TX angle. Okay. So just to test our understanding of the monostatic case. So monostatic means I am in the 2D case. So let us say the incident wave is coming like this. Okay. So what is the angle it makes? Let us say we will just continue this. This is theta I. All right. Now it reflects back from the radar and it goes into which direction? The direction is reversed. Okay. So the reversed direction is going to be this, right. So what is the angle it makes? This is the angle it makes, theta S, let us call it, the scattered angle. So is there a relation between theta I and theta S? Can I write that theta I plus pi is equal to theta S, right. So this theta S is what I will plug in over here into the receiver angle, into the receiver part of the RCS definition. Okay. So in the monostatic case, it is already fixed. I have theta I plus pi and theta I, those are the two arguments to the RCS angle. Okay. Similarly, in the 3D case, I have to think about theta and phi. Okay. So this is just definition. All right. So should not be anything too complicated here. Now let's get into some of the details. Okay. Now the details we can take either the surface integral or the volume integral approach. It does not matter. Okay. So I have just taken the volume integral approach here. This is the field observed at a distance r prime. R prime is some general distance, right? This is what I have. Now those of you who have programmed these Bessel functions, Hankel functions will know that to evaluate a Hankel function or a Bessel function is a slightly expensive operation. When you ask MATLAB to compute Bessel function, Hankel function, it has to do an internal calculation to give you that number. It is not like asking the computer to calculate x square or 2 into x. Okay. Now when people start calculating the RCS of some aircraft, they do not want the value of the RCS at one angle. Typically you want to know what is the overall behavior. So in 2D you would calculate the RCS over an entire 2 pi radians. Okay. So you have to calculate at several different positions r prime, you have to put your receiver and calculate what is the scattered field at that point. So there are some approximations that we can use. Remember, the RCS definition is r tending to infinity, right. Now back in the very beginning of Green's function, we had actually come across this approximation. For very large x, this Hankel function looked like this. It became like a plane wave in 2D, because there is a e to the minus jk rho, and this is also what helped us to fix the which of the two incoming or outgoing waves we should keep. Remember, because my time convention was e to the j omega t, combined with this I got a outward travelling wave, right. So we have seen this expression before. Now let us just try to look at the challenges. Supposing I take this most general form of Hankel function and put it inside over here, what will happen? That every time I change my receiver position r prime, I have to evaluate this Hankel function, obviously, right, and I am giving you further information that is a slightly expensive operation. So to reduce the cost of doing that, we should use this approximate form, which is accurate as you go to larger and larger rho. Okay. So rho over here is simply this distance r minus r prime. Okay. So, if I plug this expression back into this, that is what will help me. Evaluating this is much cheaper than evaluating Hankel function, right, because it's an exponential and it's divided by root rho, right. So, this is going to be much more computationally efficient without any real loss in accuracy. Okay. So, now you can see one thing, this was in 2D, in 3D this was our Green's function with no approximations, right. So, if you go back now to the definition of your RCS, so there is a 2 pi r over here, right, and this first term over here is E scattered squared. So, if I sort of, you can imagine that this root rho is going to come out of this integral approximately, and when I square it, what will I get? I will get rho, and that rho cancels off with this r over here. As a result, what you will get is that the RCS is independent of the distance at which I am. It does not depend, it is not that it depends on the value of is it 1 kilometer or 2 kilometers. I do not get different answers each time, because that distance has cancelled off from the numerator and denominator of here. So, that is the reason why the definition of RCS has this 2 pi r over here, and in the case of 3D I have 1 by r, so to speak, right. Remember, r is going over the object, whereas r prime is tending to infinity. So, this term basically will approximately come out of the integral sign over here. When it comes out, I have a 1 by r in the denominator, I have to square it, take its mod squared, I get a 1 by r square, and that cancels off with this r squared over here. Okay. So, this is actually what motivated the definition of RCS, because you are reporting a quantity that does not, strictly speaking, depend on the distance to the object. So, it is useful. When I say this is the RCS of an aircraft, you do not have to ask me in return, but at what distance, right. It is more like a universal way to characterize this object. On the other hand, if I had removed this 2 pi r or 4 pi r squared, then I would have to every time tell you at what value of r, and I will get different values of the RCS. This is one way of getting rid of the distance dependence. Okay. So, one small sort of further simplification we can do over here, which is a very common approximation in electromagnetics. So, this r minus r prime, how do we write it? I can write it in terms of Cartesian coordinates like this. Okay. So, remember, in this integral, r is over the object, either surface or volume, and r prime is far away, correct. So, I can further write this as, so okay. And this, what I can assume is that since my object, this is, let us say, my my point r prime, right, that is where I am evaluating this, is somewhere which is far away, right. That was the definition of RCS, r tending to be very away from the object, and my object is something over here. Okay. So, this x prime square plus y prime square, I can take it to be equal to some capital R squared, let us say. Okay. So, I can write this as r squared square root. Now, I can take this common from here. So, 2x x prime minus 2y y prime divided by r plus x square plus y squared divided by r square. That is say again, yeah, this should be r, correct, this should be r. We took r, so this term over here is equal to r squared. So, I pulled out a r from this square root sign over here, right. So, this r came out from here, and this is the expression that I got. Now, from these terms, which one do you think I can ignore any one term from here, given that r lives over here and r prime lives outside. So, from these three terms, this is square dependence on x and y, and this is a linear dependence on x and y, right. So, this term is actually going to be small, right. So, I can approximate this as r right. I can ignore this term which is going to be very small, and right. Okay. So, the common approximation that is done is for amplitude. So, I have this rho term over here, this is rho, is appearing in the denominator in the amplitude and in the phase, that two places where it is appearing, right.
R dash is the distance from the origin to the receiver.
Yeah, r dash is the location of the receiver, right. So, this is rx. Yeah. For the amplitude term, what do you do? It turns out that if you make a further approximation of ignoring this term also, so you replace rho as approximately equal to r. Okay. So, you ignore this term also, and for the phase term you write rho is approximately equal to r into, you can use the binomial expansion over here, and you will get a one of the 2's cancelled off. Okay. So, this is a very common approximation that is used, and that gives you very good accuracy also. Okay. So, I mean the objective of doing all of this, it looks a little tedious to begin with, but when you get the hang of it, it's basically to simplify evaluating this expression, right. So, then what are the unknowns inside this? It will just be this chi r and phi r, which you have calculated already, which you know already, and this g term becomes very simple. It is just a plane wave term, and this rho over here we are taking it to be constant, and when we square it, so it becomes root r, and in the definition of the RCS there is a r sitting outside anyway, so it cancels off, right. So, so these are the approximations that we can do. Okay. So, this is the amplitude term and this is the phase term. So, the approximations that we make in the amplitude term and the approximations we make in the phase term. Yes, r prime is the location of the receiver.
Definition r prime should tend to infinity.
Yeah, if I have, yeah, so if I, here I have chosen the unprime, I mean the prime coordinate. So, my definition of RCS will be,
R prime
here it will be r prime, right, 2 pi. So, we will make this to be,
why are you choosing the approximation to be the same for both?
you can, but it I am giving you even, you can choose the same approximation for both, but it turns out that doing this gives you almost the same accuracy, right. So, this is 2 pi, let us call it r mod of r prime, right, and then E z scattered at r prime theta squared E z I at 0 0. That is because I had the field here in terms of prime coordinates, and this definition over here assumed it was in terms of unprime coordinates, just a small change in convention. In the definition, where does theta I come into the picture? Well, it will matter, right, because the scattered field that I calculate will depend on the, I mean when I have solved these equations to get my phi, I needed the value of the incident field, otherwise I could not have solved the system of equations. If you look back over here at our equation, the incident field appeared over here, right. So, depending on the value of the incident field, my current inside the expression got set. So, implicitly the solution that I get depends on which angle I am illuminating the aircraft from, right. So, that is why it is a function of theta I. This is the so origin is here inside the object. No, there is an object which is centered on the origin, okay, it is approximately in that region. Some I mean, yeah, so this is the object.
So, with respect to the origin, r doesn't go far, but r prime.
Yeah, r does not go far because it is a finite object. R prime is where my receiver is, and the definition says take r prime to infinity.